Hello dear friends, welcome to a lecture on Euclidean rings. In this lecture we shall study unique factorization theorem, which is specially in Euclidean rings. The theorem is another form in polynomial rings also, but we shall study this theorem in Euclidean rings. And I have written here statement. First we shall see the statement and then we shall prove the theorem. Let R be a Euclidean ring. We have studied earlier what is meaning of Euclidean ring, having two properties with D function defined and another second property is of division algorithm, and A not equal to 0, non-zero and non-unit in R. We consider an element which is non-zero and non-unit. Suppose that this element A is expressed in this form. A is written as product of these prime elements in two ways, and this also we have studied in our earlier lecture, and that theorem was factorization theorem. A non-zero element in an Euclidean ring, is either a unit or can be written as a finite number of product of prime elements. You may refer that theorem also, and thus here we have written A as product of prime elements in two ways, P1, P2 up to Pn, and the same element A is written as Q1, Q2 up to Qm, where these Pi's and Qj, where I takes value 1 to n and j will have the value 1 to m. Pi and Qj are prime elements of R. Then n is equal to m. If this is written in this form two way, then this number of prime in first expression is same as number of prime elements in second expression. N is equal to m. These factors are the same, prime elements are the same in number. N is equal to m. Number of prime elements are the same, and each Pi, that I takes value from 1 to n, is an associate of some Qj. J takes value 1 to m. That, and the second thing is, there are two things in this unique factorization. That means the number of prime elements in both expression, the number is the same, that is n is equal to m, and each prime from this expression is an associate of some prime from second expression. That each Pi is an associate of some Qj, and conversely each Qj or each Q is some associate of some P. That is the meaning of this theorem. So this we shall have to prove. So if you consider a simple example of Euclidean ring, which is a ring of integers, that is Z, with usual addition and multiplication, then we know what are the prime elements in this ring of integers, that non-unit. And again the prime element we have defined as, say, P is a prime. If we write P as equal to AB, then either A or B is a unit, then that element is known as prime element. So prime elements in Z are, see, these are with positive and negative sign, plus or minus 2, plus or minus 3, etc. These are prime elements in Z. And now if you consider any non-unit in R, any number in Z here, that is the ring of integers. Suppose I shall consider an element as 30. Then this can be expressed as in the product of prime elements. And if you write this in two ways, then what will be the relation between the two expressions? So 30 we can write as, it is simple, 2 into 3 into 5. this may be P1, P2, P3 can be considered. And the same we can write like this also. Say I shall write -3, -2 and then 5. So it is the same. Now what is the relation here is this the number of prime elements here, which are 3, and here also these are 3, and relation between these is they are associate. So 2 is associate of -2, 3, the order may be different. 3 is associate because it is commutative, and therefore we can write in the same order, or we can change the order. Some P is an associate of some Q here, and not necessarily in the same order. So 2 is associate of this -2, 3 is associate of we have studied associate elements also. A and B are said to be associate if we can write A is equal to UB, where U is a unit, some unit in R, and that means 2 minus 2 are associate. The negative of each other are associate in simple ring of integers, and 3 is associate of -3. 5 I have written the same, 5 is also associate of 5, or this may also be written as say 3 then -2 -5, or we can write -5 then -3 and 2. So these are the different expressions, but the prime elements, number of prime elements are the same, 3, and the relation is these P's are one expression, and in the second expression the elements, prime elements are associate. Some prime is associated with another prime in the second expression. So this is the meaning of the theorem in these two expressions. Now we shall prove it. So we shall consider the expression of A. We have A is equal to, it is supposed or given, A is having the expression P1, P2, Pn is equal to Q1, Q2 up to Qm, and now we have obvious relation as this P1 divides P1, P2, Pn. It is obvious because it is a factor here. P1 divides this, so just as 2 divides 2 into any product, say, because it is a factor here, and therefore P1 divides this expression P1, P2 up to Pn, and since P1 divides this, and this is equal to Q1, Q2 up to Qm, therefore P1 divides this side also, and therefore P1 divides Q1, Q2 up to Qm. But you see, these are prime elements. All these are prime elements. P1, P2, Pn, we have written here prime elements. And we have proved earlier a theorem, as if P is prime and that prime divides product, some product of 2 or more elements. So this result we have, if P is prime and P divides AB, then this implies P divides A or P divides B. It must divide at least one of them, and therefore if P1 divides Q1, Q2 up to Qm, this is generalized, then P1 must divide one of Qi. Then P1 divides Qi for some, or we can say P1 divides Qi for some Qj. Qi we have written here, and but you see, these are primes, these are prime elements, and therefore they must be associates. But P1 and Qi are prime elements. And therefore they are associate of P1 and Qi are associates. Associate elements, or they are associates. What is meaning of associate? A and B are said to be associate if we can write A is equal to UB, where U is some unit in R, and therefore we can write as, so therefore we can write P1 is equal to U1 into Qi, where U1 is unit in R. U1 is some unit in R. So thus we have the expression for P1 as, or in place of P1 we can write Qi as. See, they can be written as, if A and B are associates, then they are associate of each other. Either we can write P1 as in terms of Q1 Qi, or we can write Qi as. So in place of we want to write like this, Qi as U1 into P1. They are associate of each other. Say just as 2 and -2 are associate of each other, and therefore we can write 2 is equal to -2 into -1, or -1 into -2, or we can write -2 as -1 into 2, like this. So therefore we can write here as Qi is equal to U1 into P1. Now we consider the same expression here. See, we have A is equal to this P1, P2, Pn, etc. Now A is equal to P1, P2 up to Pn, and this is equal to Q1, Q2 up to Qm, but in between there is Qi. Qi is an element in this expression. Qi or Qj, any suffix can be used, and so I shall write here as Qi, and that is continued up to Qm. So we have expression of this type, and now this Qi is written as U1 P1, and that we can write as first element or first factor, because it is commutative. It is Euclidean ring, it is commutative, and therefore this we can write P1, P2 up to Pn, and this is equal to, this Qi expression is U1 P1. I shall write it first, U1 P1, and then we will continue the same Q1, Q2, but you see this we have written as first element here, and therefore earlier to this element, the element will be Qi minus 1, suffix, earlier suffix is I minus 1, and next will be I plus 1, and that is Qi plus 1, and then it will be continued up to Qm. So this is the expression. That means one element here from this second expression we have expressed as U1 P1. Now this is Euclidean ring, and it is an integral domain, and cancellation law holds in integral domain. Now which element can be cancelled? The same element is P1. So P1 can be cancelled from both sides. Cancelling P1, we can write the expression as cancelling P1 from both sides. we have, now see, the left side will be now P2, P3 and so on up to Pn, and right side this P1 cancels, from either side, and right side will be U1, Q1, Q2 up to Qi minus 1, Qi plus 1, because we have replaced Qi here as U1, P1, and this will continue up to Qm. So thus we have cancelled out P1 from both sides, and now we repeat the same argument with P2, and P2 can be cancelled, and continue this process for P3 and so on. So we repeat the argument or process. For P2 and so on. Now what will happen if the n is less than m? Then all the elements from the left side will be cancelled, and the left side will reduce to 1, or left side will become 1. If n is less than m, the left side elements will be cancelled and the left side will become 1. So if n is less than m, the left hand side will become 1. And what will happen on the right hand side? On the right hand side, every time one unit will be introduced. So some unit there will be a product of some unit elements, some unit, and some Qi which are excess, because we have written m is greater, excess over m, and the right side. And the right side is a product, or reduces to a product. Product of some units in R and some Qj's, excess over n. Excess of excess m over n. That means suppose this n is 7 and m is 10, then 3 Q's will remain on right side, and 3 units, 7 units will be there. So that will happen. But what will be this in this case? The left side is 1 and the right side is product of some prime elements and some Qj's, some prime elements Qj's. But then product of prime elements will be equal to 1. Then 1 is equal to product of some prime elements. And this is a contradiction. Product of prime elements cannot be 1 because prime is a non-unit. and therefore its product cannot be equal to 1, and that means this supposition is wrong, which is not possible, or which is a contradiction. Which is not possible, or we can write which is a contradiction. Therefore, n cannot be less than m. Therefore, n is not less than m, and therefore m must be less than or equal to n, and thus we have m is less than or equal to n. M cannot be greater than n, and therefore m must be less than or equal to n. Now what we can say is repeat the role of P and Q. See, this can be interchanged. If we now suppose Q1, Q2, Qm on the left side expression and P1, P2, Pn as on right side expression, and we repeat the same process, then in that case we will have n is less than or equal to m. So interchanging the roles of P and Q. Similarly, interchanging the roles of Pi and Qj, we get n is less than or equal to m. We get n is less than or equal to m. And now combining these two, earlier we have m less than or equal to n, and here we get n less than or equal to m, and this is possible only if they are equal, and thus so therefore we must have n is equal to m. So this is the case, n is equal to m. And what is the remaining is that we have already stated that each Pi is an associate of some Qj. Earlier we have said P1 is associate of some Qj, and conversely Q is an associate of some P. And also we have started our proof with the same thing, that is P1 divides this, means P1 divides some Qi or Qj, and therefore P1 is associate of Qj, and so on. So that means some P is associate of some Q, or that can be written as Pi is associate of some Qj. Also each Pi is an associate of some Qj, and conversely, interchanging the role, we can get the converse part, and conversely each Q is an associate of some P. So this proves the theorem. So thus we have proved a theorem which is known as unique factorization theorem in Euclidean ring. If a non-zero, non-unit element has expression which can be written as product of prime in two ways, then the number of prime elements are in two expression are the same, the number is the same, n is equal to m, and each P is associate of some Q and converse part. That we have proved in this theorem. So I hope you can understand this. Thank you for watching the lecture.